Okay, hello and welcome to Beam call number 3. This call will be dedicated to the peer-to-peer networking layer, and we have many speakers today, 8 speakers. So let's get started as quickly as possible. What I'm going to do is share a set of slides with a few social updates to get us started. Okay, so social updates. The first thing that I wanted to mention is that we are going to have a Beam Day in Cannes on June 29th. So that's one day before the start of EFCC. We have a space. There's limited capacity. So if you'd like to join, please DM one of the coordinators. We have a Luma page. We're giving preference to the devs and researchers, but anyone is welcome to join if we have space. Also, a few useful links and QR codes that I wanted to share from last time as well. And then another event that I wanted to highlight is the very first ETH Proofs call, which will happen on April 25th at 2 p.m. UTC. ETH Proofs has a lot of synergies with the Beam chain because of the accelerationism of zkVMs. That's kind of happening in parallel to all of the R&D that we're doing with the Beam chain. And there's a Telegram group that you're welcome to join if you'd like to join these calls and the discussion in general. So here is a copy of the slide from last time around the tentative call schedule for 2025. We've had call number 1 with social updates, and basically calls 2 to 6 will be high-level research updates on some of the key topics. And today, peer-to-peer networking is the key topic. And then towards the second half of the year in Q3 and Q4, we will have specking calls where we will first start with the subspecs and then put everything together in a holistic feature complete Beam spec. So this is the list of today's presenters. There's going to be eight of them. And we're going to be extending the call from 1 hour to an hour and a half to fit everyone. And these are the topics that are going to be discussed. So first of all, we're going to start with Emil, who's basically giving a talk, which is a continuation of Beam call number 2, the previous Beam call, on some of his work around shorter proofs. And then we'll kick the peer-to-peer networking discussion with first a talk by me on permissionless aggregation. And then we're going to have 4 talks that are basically looking at potential improvements to the gossip layer. Age will talk about generalized Gossipsub. Pop will talk about Gossipsub 2.0. Camille about the grid topology, and Lee on set reconciliation. And then we'll close off with 2 quick updates on implementations of libp2p in 2 new languages. One is in C and one is in Zig by Mihir and Bing. And the final social update that I wanted to give is that the Ethereum Foundation is building a networking muscle, a networking team internally. We've had Pop at the Ethereum Foundation for a while now. And just a few days, maybe a few weeks ago, Marco came in, and we have a third person who will be joining us this month, a very early contributor to libp2p, and hopefully this team will be able to help accelerate the Beam chain networking as well. And yeah, without further ado, what I want to do is start with Emil's first presentation, which again is a continuation of last week's call. Here are his contact details, and you can find some of his work on GitHub. Emil, if you are on the call, feel free to share your screen and get started.
Yes, thank you. One sec. Okay, can you see my screen?
Yes.
Okay, thank you. Hello, everyone. So I'm going to present a technical note on how to achieve hash-based snarks with short proofs, which is particularly interesting for building post-quantum aggregate signatures. To do this, we can use the Weir polynomial commitment scheme, PCS for short, as a replacement for Fry. This gives us smaller proofs. You can think of a Weir proof from between 100 to 200 kilobytes. And also, there is the fact that Weir can be used either as univariate or multilinear, which will be useful as you will see. So I think there are three ways of leveraging Weir in the context of the R arithmetization. First, we can use Weir as a direct replacement for Fry, committing to each univariate columns as well as the univariate quotient polynomial. This would automatically give us shorter proofs, and it's simple. Other possibility, we can use the Weir's multilinear commitment capability by encoding all the univariate columns into a single big multilinear polynomial using the first variables as selectors, as well as using Weir in its univariate mode to commit to the quotient polynomial, and we would get a proof which is roughly 2 Weir openings. But we can do even better. We can get rid of the quotient polynomial. Indeed, if we commit to the whole R table as a big multilinear polynomial using Lagrange basis, we can use super-Spartan sum check, it's a paper, to prove the validity of all the R constraints without committing to any additional polynomial different than the R table itself. And in the end, we can get a snark, a hash-based snark, whose proof is basically dominated by only one Weir opening. So you can think of 1 to 200 kilobytes, which is approximately 10 times better than Plonky 3. That's the conclusion. Thank you.
Amazing. Thank you so much, Emile. And from my perspective, kind of the story here is that a month ago, Emile just appeared out of nowhere on my radar, and in just a few weeks, he's been implementing post-quantum signature aggregation with best-in-class proof sizes, but also best-in-class complexity of the code base. So it's only roughly 6,000 lines of code for the prover and the verifier combined, and yeah, looking forward to working more closely with Emile. Thank you so much for the short presentation, Emile. Okay, let me go back to my slides and continue with the start of the peer-to-peer networking content. So the following is, a straw man. It's a proposal. You should think of it as the beginning of the discussion, not the end of the discussion. So one of my key goals is for the peer-to-peer networking layer to be potato friendly. And what do I mean by a potato? I mean a computing device which is very, very weak. It could be a phone, it could be a Raspberry Pi, or it could be a watch. And in some sense, this is what makes the problem difficult, that it's potato friendly. But on the other hand, I'd like the peer-to-peer networking to be simple and pragmatic. And there's a few ideas here to simplify our lives, and I will go through them one by one. So the first idea is to reuse libp2p. So we've done a lot of work with the beacon chain to build a robust set of libraries written in many different languages. And so at first approximation, what I'm suggesting we do is that we just reuse all of the work or most of the work that has been done already at the peer-to-peer networking layer. And that includes Discovery v5 and Gossipsub. And one of the pieces of good news is that data availability sampling is kind of pushing the limits of Gossipsub, which is kind of leading to some more R&D and innovation at those layers. And maybe the beam chain can make use of these improvements as well. So there's some nice synergies there. Okay, simplification number 2, which might sound like strange, is actually to stick with pre-quantum security for the networking layer. So at the networking layer, you have some channels that are authenticated using pre-quantum keys. And my suggestion is actually to stick with those pre-quantum keys up until the point where we actually do have an active quantum attacker. And the reason is that these keys are ephemeral, so they don't live long. They're very low value, and the whole system is off-chain. So because it's not enshrined in consensus, it's something that we can upgrade relatively easily without having to do a hard fork. So basically, my suggestion is that the parts that are enshrined, the validator keys, those need to be, very robust early in advance, because it takes a very long time to do hard forks, but also for the validators to upgrade their setup. On the other hand, the peer-to-peer networking libraries can stay pre-quantum for much longer. Okay, simplification number 3 is that I'd like to make this pragmatic assumption that not all of the nodes are potatoes, that some small subset, for example, 1/8 of the nodes are actually reasonably powerful computers. And my definition of reasonably powerful computer is something like a MacBook, a laptop which has a relatively beefy CPU and potentially a CPU and potentially a GPU to help as well. And one of the things that I'm not assuming is that there's any actor that has like a really powerful internet connection. So all of these actors on home internet connections, the vast majority are potatoes, but a small subset are actually like slightly more powerful. And these slightly more powerful entities would be the ones that would be doing the heavy lifting, the aggregation. So unlike with BLS, where even potatoes can do aggregation, unfortunately, with post-quantum signatures, the machinery is more expensive, and it's likely that we won't have Raspberry Pis and smartwatches be powerful enough. So it's kind of a requirement that there's at least one actor which is not a potato. But my assumption is basically that there's at least 1/8 of the nodes. And the way that I would go about it is that the clients would run some sort of a dummy benchmark at runtime. For example, when they open the client or on a regular basis, and they just try and aggregate proofs. So for example, they take signatures. They take 1,000 signatures, and they measure how much time it takes to aggregate those 1,000 signatures. And if the time is small enough, then that node is kind of automatically enrolled and listed as an aggregator. So it would be a default on parameter, and if you want to opt out, then you need to specify in the flag that I'd like to opt out to be an aggregator, even if I'm not a potato. Okay, simplification number 4 is that with the aggregation technology that we have for post-quantum signatures, we actually have more power than BLS. So we have the ability to do recursive aggregation, which is something that is fundamentally limited with BLS. And this allows us to do 3 things. One is this optimization, which I call local greedy aggregation. So the idea of greedy aggregation is that if there is a window of time where you receive signatures, you don't have to wait until the very end of the window to start the aggregation process. What you can do is kind of partly through the window, just aggregate whatever signatures you've received. And then as you receive more signatures, well, you just append to what you've already aggregated. And so that allows us to minimize latency. Another interesting thing is that recursive aggregation allows for collaborative aggregation. So right now we have these designated aggregators with BLS, and you can think of them as silos, right? Like all of the work that they're doing in the context of aggregation is local to them, and they're not sharing any work with anyone else. And then what we're doing is we're taking these aggregate signatures and concatenating them in the beacon blocks. Whereas with recursive aggregation, you can have one person do a bunch of aggregation, and then anyone else can permissionlessly kind of contribute to the aggregation. And then another nice property here is basically a follow-on on collaborative aggregation, which is that if you have an aggregator who is censoring a minority of attesters, well, anyone can just take their work and add on the minority that's being censored. Okay, and then simplification number 5. This is not really a simplification at the peer-to-peer networking layer. It's more a simplification for the whole beam chain, whereby instead of having this complicated way of sampling the active validators, we just have a cap on active validators, and we just take the validators that are the largest within this cap. But in my opinion, in order for the strategy kind of to be very attractive in the long term, we want to have a very, very high cap. And so my tentative goal here would be to have 1 million active validators per slot. So what I think we can potentially do is have a proof of concept in 2025 with only 8,000 active validators and the aggregation all within one slot. But we should be thinking about the long term. And the good news is that I believe there's an opportunity to grow relatively fast to this 1 million active validator goal, basically thanks to Nielsen's law. So Nielsen's law says that every 2 years, roughly speaking, internet connections will double in bandwidth. And the reason why I have a square here is that the design that I'm suggesting has this property of quadratic scaling, meaning that every time internet connections improve by a factor of 2, well, actually, we have an opportunity to increase the number of active validators by a factor of 4. And so over a period of roughly 6 years, from Genesis onwards, we could potentially get to 1 million validators if we 4x every 2 years. And if we start at Genesis with, for example, 32,000 validators. Okay, so what exactly is the high-level design that I'm suggesting? Well, in some sense, it's very, very similar to what we have today. So today what we do is that we take attesters and we split them up into disjoint subnets. So if we have 8,000 validators, what we could do, for example, is put 1,000 validators in each subnet and have 8 of them, subnet 1 to subnet 8. And the attesters would be sending the leaf signatures into those subnets. And then you basically have a signature gossip that we have today in each subnet. Now, from here onwards, this is where things change a little bit. So basically what I'm suggesting is that we have this notion of the local aggregators. So of those 1,024 attesters, some subset of them, let's say roughly 1/8, so roughly 128 of them, would be powerful enough to contribute as aggregators, and instead of being designated to be aggregators, they can just permissionlessly just help out. And so what they would be doing is that they would be observing the signatures that they receive at the gossip layer and aggregating them on the computer to form local aggregates. So this would kind of be phase 1 in a level 1 in a 2-level aggregation. And then once we have the local aggregates that are within these small committees of 1,000 attesters, we would have this global aggregate. So again, we would have some number of aggregators who would help out because they're powerful enough to take the aggregates, for example, one aggregate, the best aggregate per subnet, and then aggregate the aggregates recursively to generate these global aggregates. And ultimately, what do we want? We want one of these aggregates to be proposed by the next L1 proposer. So what the proposer for that slot will do is that they'll connect to this global topic for the global aggregates. They'll pick the aggregate that has the most weight, the most number of ones in the bit field, and ultimately propose that. Now, happy to take questions here, but also happy to just continue on and basically zoom in a little bit to what's happening within one of these subnets. Now, there's a lot of design space as to what exactly can happen within those subnets, but one of the ideas that I'd like to suggest is that we have this bit field first approach. So because we're dealing with fairly large objects, each post-quantum signature is 3 kilobytes, and each aggregate is like, over 100 kilobytes, let's say 128 kilobytes. Like these are things that we don't want to be redundantly and needlessly downloading and uploading. And so the bit field first approach basically says that every node will advertise to all of their peers what signatures they have as a bit field and what is the best aggregate that they have also as a bit field. And these bit fields are tiny, right? They're 1 kilobits, which is 128 bytes. So like tiny messages that get shared between the peers. And then if a peer wants to get signatures, download signatures from another peer, basically there's this message which says, I want signatures, and the bit field will specify the signatures that they want. So if this peer already has a bunch of signatures, then the corresponding bit field will be 0 because they don't want to download them needlessly. And so this other peer would just return the list of signatures. So these are heavy signatures, 3 kilobytes each, but they're only downloaded if specifically requested from another peer. And then you can have the exact same logic for the aggregates. So again, you would only request an aggregate if you specifically wanted it, as opposed to being, it's more of a pull than a push mechanism. Okay, happy to pause here. I do have a final slide on the updated mind map, but just wanted to open it up for questions really briefly.
On this particular slide, Justin, where you have like the proposer pick one signature out of the many signatures in the end, does this allow griefing attacks? Like, someone, an aggregator, having a batch of validators on the side, hiding them from the other people, and then pumping up their aggregate signature to be highest weight. You know what I mean? We explored this in the Horn post quite a bit, and it felt like when in the end you choose the best out of many, there might be attacks that are possible.
Great question. So one of what I described here is basically this very simple algorithm, which is that each of the global aggregators, they take the best signature from each subnet, and then they aggregate, and then you call it a day. But really what we want to be doing is something a little bit more sophisticated than that. In particular, the global aggregators can learn among themselves. So what a global aggregator can do is basically pick the best that they've seen here and add on anything that they have, which is not in the best from the other global aggregators. And so this goes back to this notion of censorship, which I think is what you're referring to here. So you could have a global aggregate, which is the best in the sense that it's heaviest, but it's kind of censoring a minority. Well, as soon as you have a censoring entity who's publishing the best, well, that can be kind of boosted to include the censored attestations as well. So that's kind of a nice outcome of the recursive aggregation. Okay, Kev is asking why 1 million validators and not 500,000 or 2 million? Just because 1 million is kind of a round number. Roughly speaking, it would give us the same minimum amount of ETH that we have today, like 32 ETH. And the reason is that we have roughly 128 million ETH. If we have a million validators, that's 128 ETH per validator. If you have the least amount of consolidation in the worst case, I think more likely than not, we're going to be capping the amount of staked ETH to half. So that's already half to 64 ETH per validator. And more likely than not, more than half of the stake will not be controlled by an attacker that's trying to spread all of their ETH. So this is where you get the same 32 ETH minimum in order to be an attester. Okay, I'll take one more question if someone wants to unmute. Otherwise, I'll just read out one of the questions. Okay, I'll read out one of the questions. Okay, Casey says, regarding Nielsen's law, bandwidth scales, but latency is roughly invariant. Yes, I agree with that. Doesn't that matter for how we model this? I don't think it matters that much. And the reason is that, there's roughly the same number of hops that are involved. I mean, you could argue that as you have more and more attesters here, then the number of hops will grow a little bit. But if you have, for example, a mesh topology where you're connected to 64 random pairs, well, the depth of that mesh, of that graph is only gonna grow logarithmically. So maybe there's one extra hop if we multiply the number of attesters by 64, but that one hop is going to only add minimal latency. And then there's some designs out there. For example, Camille has this suggestion to have a grid topology where the number of hops is always 2. And so in these designs, the latency doesn't increase at all, actually. I mean, the number of connections will increase, but maybe the number of active TCP connections or UDP connections can grow with Moore's law, Nielsen's law as well. Just for the sake of time, I'm going to move to the next speaker, but I do want to just shout out the mind map. So the idea of the mind map is that every beam call, I add one little block in the mind map, and ultimately we're going to fill the whole slide. And so in what I've done so far is that I've updated the post-quantum cryptography mind map with some exciting papers, and I've also added the networking mind map. So the strawman basically is to reuse infrastructure we have, Discovery v5, Gossipsub, and the 2-layer aggregation that we have. And there's some alternatives that are going to be discussed in the next presentations, and there's some implementations that are also happening in parallel to accelerate some of the R&D. Okay, and with that, I'm going to stop sharing and opening it up to the next speaker. Next speaker is Age on Generalized Gossipsub. Age, the floor is yours.
Can everyone see this?
Yep.
Okay, cool, thanks. Yeah, so my name's Adrian. I work on the consensus layer, for those of you that don't know me. It's a bit late for me, so sorry if I'm a little bit incoherent. I also have a little bit to say, so I might skip over things just for the interest of time, to try and fit inside my time slot. The first thing that I wanted to talk about is just to take a step back and look at like essentially the design space of all peer-to-peer kind of structures that or protocols that we could implement. And I think in my mind, there's three main principles that we, or I guess features that we're looking for. One is like low latency, one is high resilience, and one is low bandwidth. And I've been looking at different kinds of ways that we can disseminate like messages on a peer-to-peer network. There's one which is like a lean broadcast tree. We can think of a structure where you have one peer that sends it to two, that then sends it to three, and it propagates in that manner. That would be kind of a protocol that is low latency, low bandwidth, but it's not very resilient. You can imagine if one of those nodes are malicious, then its subtree is not going to get the message. So you sacrifice resilience, but you get low latency and low bandwidth. If you look at the other side, you've got something that's highly resilient and low latency. You have something that's like FloodSub. The message, this is where each node is connected to every other node. You're sacrificing bandwidth here. This kind of network, you have massive message amplification, so incredibly high bandwidth, but you have high resilience and low latency if you don't care about bandwidth. If you look at the bottom, you want something that has high resilience and low bandwidth. You've got something that's kind of like pure gossip. The dotted lines is representing gossip, so essentially the nodes are just messaging that they have a message. They don't actually send the message, and then anyone that wants it then requests it of them. In consensus land, we have Gossipsub, and in my mind, it kind of exists in between this triangle. It has parameters involved in it that allows you to make trade-offs between latency, resilience, and bandwidth. And at the moment, we're at the point where we're trying to optimize this protocol so that we move somewhere inside this protocol for our use case. The main point that I think I'm going to try and make in the 8 minutes here is that we were starting to make trade-offs between each of these three properties. And we're doing that specifically for some application. The Gossipsub specification means that if we make one particular trade-off, it applies to everything. It applies to all applications. So if we want to make a trade-off for latency versus bandwidth or resilience versus bandwidth for the PDAS topic, it necessarily applies not only to the PDAS topic, but to the block topic. So if we sacrifice latency, we're sacrificing it on the block topic as well. It also then applies to every other network that uses Gossipsub, like Filecoin, or IPFS. So any change that we make is going to necessarily affect everything else. And the point that I want to try and make is to try and not make that happen, like that we can target specific applications. Okay, the other thing that I wanted to talk about, which is not really relevant to this talk, is privacy. Privacy has been a long-standing thing. So we've known since we've implemented Gossipsub in the consensus layer that we don't really have privacy. We have pseudo-anonymity. People kind of think that the validators are anonymous, but it's not very hard to de-anonymize them. And because of that, a lot of our research and development, let's say, is limited, because if we propose something that breaks this anonymity, it's usually shut down as a community. So my argument here is that Gossipsub, we currently don't have privacy. And so if we were to think of a world like the Being chain, if we were going to re-engineer an entire new networking stack, is privacy something that we need? We currently don't have it. And if we were to think of a world where we just entirely sacrifice it, and we say that the validator set, we just like people register their IPs against their validator index, and we know exactly who we're trying to send messages to, we can build like network structures that are more like a broadcast tree. If we know exactly who we're trying to send to, and we're maximally transparent about that, we can kind of build something that's significantly easier to simulate, and we can really easily make trade-offs between the latency, bandwidth, and resilience. And I think this is potentially an avenue that it's worth exploring if the community is willing to sacrifice privacy. So it's something I'd be curious to look at. I'm just raising it. It's not really relevant to this talk, but I'm just throwing it out there. Okay, so this particular talk is specifically for Gossipsub, what we have at the moment, and to do like kind of minimal improvements to Gossipsub to make one of these trade-offs for our use cases. So the way that I see Gossipsub at the moment is it's essentially a set of rules that defines how the nodes communicate, and there's different kinds of optimization strategies that Gossipsub as it stands allows you to do. You can choose essentially how many nodes you directly connect to. These are the solid lines that I've kind of drawn here. You directly send messages. It's called the mesh in Gossipsub. You have these configuration abilities that allows you to choose the size of these things. You can choose like how many do we actually gossip to? How do we actually form the mesh or the topology? Is it more like how does the broadcast tree look? How often do we gossip and who do we gossip to? These are all kinds of configuration parameters that each node on the network can make themselves, and they can still be perfectly compatible. And I want to try and make the point that each of these configuration settings essentially is a trade-off in that original triangle that I was trying to make. And these kinds of networks are very hard to simulate real-world networks, which is something I've learned over the years. I'll get to the next slide. Oh, I'm drawing. Okay, I'm back. Okay, so I'm going to give some example strategies. One is Episub, something that I worked on a couple of years ago. The idea in this is that the mesh, which is the solid lines, is dynamic. It adjusts over time. The way that it does that is essentially you have your local view of the network, your local peers. Statistically, you look at which ones are sending you messages quickly and which ones are sending them duplicates or slow, and you try and adjust your mesh to be the most efficient as you can to try and get statistically a very efficient broadcast tree in a global view. So the idea is to try and build like this efficient broadcast tree based on statistics on how often you see messages. The end result of this is that when I did finish this, we didn't actually have really good simulation infrastructures, and I wasn't convinced that it's strictly good in every possible network. So Filecoin, IPFS, if we were to actually put this into the specifications, I wasn't convinced that it always works. There were some cases you could set some configuration parameters where it would be worse. And ideally, we want something that could automatically configure itself. Another example is Gossipsub v2, which there's going to be a talk on directly after this, so I'm not going to go into it. But as a very high level, it has like a random dynamic mesh. So the idea is to create a parameter which represents like a coin toss or a probability of whether you gossip or not. So when you send a message, whether it's going to be a solid line or a dotted line. So the idea is to parameterize Gossipsub versus directly sending. And this is a trade-off between latency and bandwidth, which is an idea proposed for PeerDAS. In the interest of time, I'll skip this, but it's very hard to simulate real-world networks. So if you see simulations, treat them with caution. So what I think the problem is that because it's hard to simulate these things, it's hard to know what we should specify and put inside the specification. Something that might look good, if we specify it, it's hard to unspecify, I guess. The optimizations and trade-offs are often network specific. So something that we're looking at to optimize inside Ethereum might not work for Filecoin or IPFS or something else. So this was one of the main reasons I didn't push really hard for Episub. Optimizations currently will apply to all topics. So if we try and find a trade-off that works really, really good for the PeerDAS topic, it might not necessarily work really well for the block topic. So if we want to trade latency for bandwidth in PeerDAS, we might not want to trade latency for bandwidth in the block topic, for example. If we spec one of the trade-offs into the Gossipsub specifications, it can potentially limit our design choices in the future. So if we go down one path, maybe we can find that another path works better in another application, and it would be hard to then do that. So an idea that I'm suggesting is something that just a quick name is Generalized Gossipsub. But the idea is we still specify the messages that the nodes interact with. We call it like essentially the core specification, but we modularize all of the trade-offs essentially that we can make. And these modules, we call them strategies. They can apply per topic and at per time. The modules are optional at the spec level. So each network, Ethereum or anyone else can specify add or remove their own ones, and it only directly applies to them. The other points aren't that important. So the general idea, there's a number of benefits for this, but if they apply per topic, it allows you for things like we can come up with a trade-off that works well for PeerDAS, for example. and we can apply it only to the PDAS topic. We can have a different strategy that works for the block topic, and we can apply it to the block topic. We can have something that works when nodes are bandwidth constrained. And if you find that your node is is severely bandwidth constrained, you can switch to a different strategy that might be better suited that's for bandwidth constrained nodes. So it allows you to essentially modularize this thing. I think I'm over time, but these are the number of reasons I think this might be good. I'm happy to answer any questions, or if anyone's interested to hit me up. Yeah, I'll leave it there. Thanks.
Thanks, Sage. Really enjoyed that talk. Any questions for Adrian?
Yeah.
Go ahead, Kev. I think you muted yourself.
Sorry. Can you hear me properly?
Yes.
Yeah.
I guess if it's hard to simulate, does that mean that most changes that get added to the networking stack are just tested in production?
Partially. So we test on testnets. The testnets network is different to mainnet. Even when we test on testnet, we can't control all the nodes on the network. So some of the problems that we run into is that we've got different versions of different nodes across different networks. So I don't know of a way of not to test in production because there's no real way to simulate mainnet. So yes, in a sense. I mean, we can get a good idea with simulations, but it's not the end story. I can give you examples, but I'm not sure if that's useful.
One question I have is, have you started speccing the generalized Gossipsub?
Yeah, so in my mind, so I wrote a proposed specification, but it doesn't really change the specification. There's no real engineering effort. It's mainly an engineering refactor. You can just refactor Gossipsub as it is so that you modularize the changes that we might want to make. So it allows you to just add and replace different potential trade-offs. So the idea with this is, there does exist a specification. I've put it here. Specification in inverted commas. It's not polished and it's not finished. It just shows the idea. My idea is to implement it inside Rust p2p. It's as a first step to allow us to do a lot more simulations and testing because we have these modules, let's say, that we can adjust and simulate and see which works.
Thanks again, Adrian. Next up, we have Pop, who will be talking about Gossipsub 2.0. Pop, the floor is yours. Adrian, if you want to stop sharing. Thank you.
Yeah. Okay, let me share the screen. Okay. Can you see the slide?
Yes.
Okay. Let's talk about the current version of Gossipsub first, right? Maybe like some of you don't know yet. When you have peer, right? You have two kind of peerings. The first one is like the mesh peering, like the solid line here, and another one is like the non-mesh peering, right? The light line here. Yeah, so there are two kind of peering. And in the current version, when you publish the message, right, and like when you publish the message, you send the message like to the mesh peer, and when you receive the message, you also forward the message like to your mesh peer as well. In this slide, you will see the the solid line is a mesh peer, right? So the message will be sent from the mesh peer. So if the degree of the mesh peer is like 8, so you will receive like around 8 copy of the message, right? And that is bad because you don't need like 8 copies, right? You just want only like 1 copy, and that is enough, right? So we will waste bandwidth for this, and that is a problem that we are going to solve in the next version. Yeah, in the current version there is also something called like gossiping. So sometimes you will receive something called I have from the non-mesh peers, and when you get I have, right, you check the I have control message like come with the message ID, so you will check like if you have already seen the message with that message ID, and if you have not seen it yet, you just send I want out, right, and then you will get like the message back. So this for the this serve as like a shortcut. Like for example, if you don't get the message from the mesh peer, like at the heartbeat, right, you will get the I have, and like it serves like a shortcut that okay, maybe you are too far away from the publisher. Yeah, that's it. Yeah, so how we solve the duplicate, right? So instead of like when you receive the message, instead of sending the message right away to your mesh peer, right, you just send like something called I announce. So I announce is like a lot shorter than the message, right? So it shouldn't like consume too much bandwidth. And after that, you will send like the I need control message, but it's very important that you send like only one I need, right? Yeah, because after you send I need, like your peer will send the message back, and because you send only one I need, and so you will get only like one message back, right? So by doing this, you will get like only one copy of the message, right? And you can also see that I will send like I need to the first peer that send me the I announce first, right? Because that is the fastest way. Yeah, but there is a problem in this design because when you send I need, right, your peer may not send the message back, right? And if you send I need only like to one peer, right, and like that peer doesn't send you the message back, like you will never get the message, right? And that is a problem. And so we need to have like something called a timeout. So if I send I need, and after the timeout, like let's say 1 second, I don't get the message back, I will send I need like to the second peer that send me the I announce. Okay, that makes sense. Yeah, and yeah, and you have to configure the timeout like very carefully, because if you set like the timeout like too high, it may delay like receiving the message, right? Because if I send one I need and like more than one peer like don't reply to me like at all, I will waste like a lot of time. Yeah, that is a Gossipsub v2. That is idea. So you can see that if the timeout like doesn't occur at all, so everyone will be guaranteed that you will receive like only one copy, right? Because you will send only like one I need, and you will always receive the message like in time. So the timeout has to be configured in a way that every honest node like can like follow. So it like you cannot set the timeout to be something like 100 milliseconds, right? Because that is like too low. And like when for example, if you are in like in Europe, right, and like you ping someone in Australia, it will take up around like 300 milliseconds already. Question?
Yeah, I guess like in order to remove the timeout, one thing that could potentially be done is to use erasure coding, right? So let's say you have 3 pairs that have each done the I announce. you erase your code, your message, and then you have each peer send like roughly 1/3 of the chunks. Or maybe they send a little bit more, so that if one of them just doesn't send their part, then you'll still be able to reconstruct the full message. So you solve this timeout issue.
Yeah. Actually, Potas is working on the random linear network coding, right? So there is like an ongoing research like on that stuff. But yeah, it's like it's more complicated. But it yeah, we have to consider like which one to use later. Yeah. Yes, and instead of sending only I announce, like we also you can configure the parameter like to like how often you will send like I announce, and like how often you will send like the message right away. So instead of sending one of the one of them, you just like you can just like mix them. For example, currently in the spec, in the spec in the PR, you will toss a coin like before forwarding the message. You will toss a coin like with some probability. Like if let's say you will send I announce like with this probability, and otherwise you will send like the message right away. So you will send I announce like with probability the announce over D, and you will send the message like with the probability like 1 minus that. Yes. And we did a simulation. You can see that when you do this, right, you will waste like 1 round trip time, right? Because when you send I announce, right, you have to wait for the I need before sending the message right away, right? That seems bad, but it's not that bad, because yeah, from the simulation I will show later like why it's not bad, but you have to know that you will waste like 1 round trip, right, for the forwarding. If you just send the message right away, right, you will not like waste 1 round trip. Yeah. So we did a simulation for that. This is we have like 3 scenarios. The first scenario is like the D announce is like 0. It means that I will never send I announce like at all. I will send only like the message, right? And this one is like D is equal to 8, and D announce is 8. It means that I will always send like the I announce, like and this one I will set the announce 7, and D is equal to 8. So it's like I will send I announce like with like 7/8 probability, right? And like I will send like the message like with 1/8 probability. And for this one, I try to mimic the 4844 scenario. So each message is like 178 kilobytes, and you can see here that the graph is about the propagation time, like the arrival time of the node, right? It is a CDF, and each line corresponds to each number of messages. Like you can see that the 64 message here is like has the worst arrival time, right? And you can see here that for the number of message, right? This line the bar line here is 32 messages, right? And it's exactly the same pace as like 64 messages here for the announce 7 and 8, right? So I assume that we can like double the bob count from the simulation result, right? But in the real world, we have to do like more rigorous testing. But this is the primary result that we can like get some intuition first. yeah. And this is the number of duplicates. You can see here that okay, if D announced is 0, right, and like D is 8, so on average you will get like 8 duplicate, right? And okay, on average you get like 7 duplicates. So this is like the number here is like large. And for the announced 7 and 8, the number is like a lot lower. So it's like yeah, it's close to 0, but you still get like duplicates because like sometimes the timeout occur, like sometimes you will get the message like from I want instead of like I announce I need, right? Because I didn't remove the I want mechanism yet. Yeah, and this is for the small messages, and is yeah, you can see that the performance is like worse because you send like more control messages, and if the message is like too small, this one is like each message is like 1 kilobyte instead of like 128. So you can see that the performance is like worse. And the last one is like we also simulate the malicious scenario. It's like we simulate with variable percentage of nodes that are malicious. Malicious node mean like you will not reply to like I need at all. You just let the timeout like happen, and this is like the results. Is like yeah. And yeah, I'm a bit over time, so maybe like I will go like yeah faster. You can see that you can see this result in the e-research post. And yeah, the further improvement is like if the timeout occur, right? So because we set the timeout to allow our honest node to follow. So if the timeout occurs, so it means that it's likely that peer is like malicious. So maybe we should downscore them. And yeah, and also we have an idea of like choke, unchoke. So currently the sender will decide like whether to send I announce or not, right? So but it probably make more sense like to allow the receiver to decide instead of the sender, right? Like yeah. So it's like if I want you to send I announce, I will just send you like a choke message, and like you are supposed to send me like I announce. Otherwise you will send me like the message right away. This is support that you can like read for more detail. Thank you.
Thank you, Pop. Any questions for Pop? And one question I have is, what do you think of generalized Gossipsub?
Yeah. I think the generalized sub I have looked at it, but yeah, it's like that is a bit conflict. It's like if in as far as I understand in generalized Gossipsub, you it's not easy to like introduce like new control messages, but in Gossipsub v2 we can still implement it like with generalized Gossipsub, but I have to change like the control message, but it's completely compatible. Yeah.
I would have a question if I may.
Yeah.
Yeah, so I'm doing something similar with the push pull, and then I'm using I have messages for saying that I have it, to announce that I have it, and I'm using I want to say that I need it. And I'm just curious to understand if your messages have something special in the semantics and in the handling, that because it kind of works for me, but I can imagine I'm like you optimized it better, or you differentiate it in the logic. But I didn't need new messages. I could just use the I have and I want in the same sense as you are using the I announce and the I need.
Yeah, actually when we wrote the spec we found like many distinction between like I announce and I have because I have like it sent at only the heartbeat, right? And there are sent like
I was changing that, but yeah, so I'm changing out sending out I have messages not just at the heartbeat, but the message itself, the messaging primitive is the same. I mean, it might make sense to have it different. I just didn't need it in the logic to differentiate.
Yeah, yeah, but you have to change the logic of I have, right? It's like, yeah, it can be done like with I have, but you just have to change the logic of I have, right? So it's like,
yeah, I also don't know which one is the better to have another message or not. I was just curious if you have some difference. We can discuss that offline as well.
Actually, because we have time out, right? And I send only one I need. So I think we should send like I need only to like the trustworthy peer because if that peer doesn't reply like to me, right, I will waste like a lot of time, right? So I think the mesh peer like are more trustworthy. So that is another distinction that okay, I would like to send the I need to the mesh peer instead of like sending like to some random like non-mesh peer.
Pop, in the interest of time, I'll cut the discussion here. But yeah, would love to continue the discussion offline. We have two more longish presentations, one from Camille on the grid topology and then one on Lee on set reconciliation. Camille, the floor is yours for the grid topology.
Great, thanks. Hopefully you can see the slides.
Yes.
Yeah, great. Yeah, today I want to discuss like how we can apply grid topology, yeah, basically for the problem that Justin described earlier. Yeah, give me a sec. So yeah, just listed some assumptions that we considered when we were thinking about that. So say like we have around 16K validators, and say like each validator generates a snark, oh, sorry, not snark, a signature of size 1.5 kilobytes. And in addition to validators, we have untrusted aggregators that generate snarks to prove that signatures are valid. Actually, the thing that I didn't consider, I think what's different to what Justin described is that, well, we imagine that we could have a limited number of these aggregators, and it's very hard to kind of differentiate who of them are malicious and who of them are really doing what they should do. But yeah. And the last assumption, I think, is also what's different from what we have currently in Ethereum validators land is that, well, validators, their addresses are known and they essentially could be matched with their signing public keys. So that means basically that they should publish their address. So previously, yeah, it was briefly mentioned that the question about the privacy, whether we should have it or not for validator addresses. So yeah, for grid topology, I think we should publish the validators' addresses, but yeah, here I try to kind of convince and explain what kind of advantages we can gain from that. In my presentation is really like two parts. First is kind of just describing what grid topology is, and second is one of the options how we can integrate it into the signature aggregation scheme. Okay, so yeah, and our goal is to kind of aggregate as fast as possible to third of all signatures. So yeah, first the grid. So the grid is really simple topology. Kind of the step 0 to kind of start distribution pattern for grid topology is to every validator to come up with the same grid view. For that purpose, they can use some common source of randomness, maybe something like Randao. And then if they have the same source of randomness and the same set of validators that they observe, then they kind of can create this two-dimensional grid lattice, and they can know the coordinates of each validator in this lattice. And then the rules for distribution are very simple. Basically, each validator maintains only connections with their column neighbors and their row neighbors. Column neighbors, I mean all validators that positions in the same column, and row neighbors in the same row. And distribution pattern can look something like that. So basically, when some validator creates a signature, it distributes it to all of its row neighbors and column neighbors. And then when column or row neighbors receive the signature, they propagate it further in orthogonal direction. So that means when, for example, column neighbor receives the signature, it propagates it to all of its row neighbors, and the same for row neighbor. When it receives the signature, it propagates to all of its column neighbors. And that means that essentially just in 2 hops after step 2, we already, in optimistic scenario, we should have all validators receive the signature from the originating validator. But we also have like 3rd step to distribute I have messages to all. So basically, whenever validator receives the signature, it also broadcasts I have message to all of its row and column neighbors. That is needed to prevent eclipse attacks, so that when someone receives I have message, but it didn't yet receive a signature, it can basically request the signature from I have sender. And also these I have messages, they are very helpful kind of to reduce number of duplicates. The most amount of duplicates each peer can get for the same message is 2, because well, they just have 2 options how to get this message. But if, for example, they already sent I have message to someone who is supposed to send this message to this validator, then well, we have no duplicates basically. If you look carefully, there are a lot of these I have messages that basically produced for each signature, but they're really lightweight. It's just some meta information about maybe peer ID and round. So yeah, I hope it's not like a large problem. So the benefits that grid topology bring is that first and the most important is that distance between any 2 arbitrary validators is at most 2 hops. If we compare that with Gossipsub, we basically observe that, well, for the same number of peers, like 16K peers, and with fan-out factor 6, we have average distance of approximately 5 hops. And then the next advantage is that, well, each signature generates basically linear number of total signature messages in validators network. If we just use the Gossipsub, then in the worst case, we would have like n times k signature messages. Before we actually, well, of course, we can apply something like I don't want or other optimizations, but because of undeterministic nature of Gossipsub, as we previously described, it's very hard to simulate and kind of come up with the optimal parameters for these I don't want parameters. And in addition to this linear number of signature messages, which are heavy, we also have n of the power 3/3 of I have messages. But as I said, they're very light, and they need it for eclipse attack preventions, basically. And last advantage is basically duplicates handling, because each peer, as I described previously, could just receive the same message from at most 2 other peers. That means, well, there are not really a lot of duplicates could happen in the network, which is why we don't have like a lot of messages per each signature. I'm saying at most, but because we have I have messages, sometimes peers just get one original message and no duplicates at all. There are other benefits that are not listed here. That's like something, for example, well, because of deterministic nature, peers know who they exactly need to talk to, so they don't need to perform costly TLS handshakes to new peers every time. Or because of deterministic nature, it's much easier to simulate these networks, kind of try to play with malicious actors and see what the effect they have on signature distribution. So and from here we kind of go to the second part where I'm trying to kind of, it's just to come up with some example of how we can apply this. Because in my assumptions, we kind of assume that, aggregators, they do not have any stake, and there might be a limited number of them, and we have no means to kind of check if they are, I don't know, malicious or not. Therefore, we can consider them untrusted, and we consider that they can freely join or leave the network. And because of that, it's very hard to join them to grid lattice. But if this requirement is not the case, and well, we can basically rely on them, joining them to grid with the validators would be great, actually. But if it's not the case, then we should come up with something else. And yeah, just some other challenges that we can have with grid topologies that, well, we cannot put all validators into a single grid for signature messages distribution, because that would mean that, well, if we calculate amount of messages, basically that means all validators should receive all signatures from all other peers. Then if we assume like 3 seconds to distribute signatures, then and 1.5 kilobyte signatures and 16K validators, then incoming bandwidth requirement would be like something like 128 megabits per second. So that's, we consider like a lot if we consider like potato validators. So we should reduce this. And the natural way to reduce is to basically not to have a single grid, but have multiple grids. So that's again somehow similar to what we have with BLS signatures aggregations, but in contrast to BLS signature aggregations, where we have like known validators who aggregate signatures, here aggregators do the work, and there are a lot of them in our assumptions. So basically what we do here is, well, validators are split into grid subnets. Inside each grid, they propagate the signatures very fast, just at most 2 hops. And then whenever validator obtained a signature, it can also stream it to the aggregators subnets. So basically, we have as many aggregator subnets topic as many validator grid subnets we have. Each aggregator can actually subscribe to multiple grids if they consider themselves kind of powerful enough so that they can aggregate from multiple grids. Inside these aggregators, Gossip subnets, I think we can further accelerate them, maybe use something like rateless ABOT for kind of this signature set reconciliation, about which I think Lei will describe later. So yeah, and then when this kind of the first level, and then any aggregator, when it collected enough signatures and produced a snark, it can propagate it further to the kind of final aggregators subnet. And these validators, again, they kind of exchange. They use Gossipsub here, so they exchange these grid level snarks, and then come up with the final snark, which they then send to validators again. And actually this time, I think we can put all validators into single grid, because each validator would propagate, for them it would be just enough to propagate a single snark to all other peers, and then just ignore all other snarks, assuming the first snark was valid. So we really don't have a lot of messages going through this final grid. And I think it's important to kind of all validators to receive the final snark, because assuming we have something like WISC with secret slot leader election, then we don't know exactly who would be the next proposer. So we basically should send snark to all validators. So yeah, that's grid. Yeah, just to conclude this, we consider it's kind of like effective protocol for distribution among validators, assuming validators know each other's addresses, and so they can, and they also have some common source of randomness, so they can form these grids. And yeah, in general, I would like kind of consider this as a building block. This grid topology, this proposal is not necessarily like how exactly these things should look like, but just hopefully I was able to describe main advantages. Yeah, of this approach. Yeah, thanks. And that's all I had.
Amazing. Thank you so much, Camille, for this very clear presentation. Any questions for Camille? I guess one question I have is it correct that this grid topology has been implemented in Polkadot, and like, do we have concrete numbers of the performance there?
Yes, correct. We have implemented that. Well, we are maintainers and supporters of C++ p2p, and we use that in our Polkadot client. Basically, in Polkadot, we use grid, and if you run a Polkadot validator, you have in your CLI command, you have like a field public address, which you should put, and which is then kind of published to everyone. And so yeah, validators, in Polkadot, we have 6-second slots. And the task they have is basically, so whenever we have a statement that some parachain, which is kind of L2, is valid, this statement should be distributed to all validators as fast as possible. I think currently in Polkadot we have, if I'm not mistaken, 600 validators, but the goal is to have 1,000, and we have 1,000 in Kusama, which is the canary network for Polkadot. So yeah, basically we have grid, so for 1,000 validators, and within 6 seconds, it is good enough to kind of distribute this statement. So the next block producer has this statement to include it into the block. I think in Beam we have requirement for 4-second slots, which is why we have. I propose to have smaller grids so that this distribution happens even faster. But yeah, that's kind of what we have.
Okay, thank you. Final long presentation is from Lee on set reconciliation. Lee, the floor is yours.
Can everyone see my screen?
Yes.
All right. Yeah, thanks. Yeah, I'll try to. Yeah, I think this looks better. Yeah, and thanks a lot for having me here, and I really appreciate Justin sending me the invite, and also the organizers for organizing this series of course. My name is Lei, and I'm a co-founder of MegaETH, but the work I'm going to talk about is from the work I did when I was a PhD student at MIT, and it's fully funded by a very generous grant from the Ethereum Foundation. So I really appreciate that. So the goal of the talk is really to kind of introduce a series of a type of very interesting primitive that is called set reconciliation, and I think it would really help like pushing the performance or kind of enhancing the trade-off of peer-to-peer protocols. I think a very good point was made in one of the earlier talks that with like designs of peer-to-peer protocols, you're basically trading off three things. One is the resiliency. Basically, how reliable can you get your messages to your peers to kind of throughout the network? Second, what's the latency? Basically, what's the time it takes to propagate the messages? And third, which is the amount of bandwidth consumed in the process. So my point is that set reconciliation could be a tool that can improve the trade-off. Like for the same amount of resiliency and for the same amount of latency you're going to tolerate, you will probably be able to achieve a much lower bandwidth consumption. So that's kind of trying to set the stage. So I will give one motivating example, which I think most of the people on this call are already aware of, which is when you gossip messages in a peer-to-peer protocol, you risk sending redundant messages. So I'm making a very simple example here. Suppose that Dave got a message which is 0xABCD1234, and Dave needs to propagate the message throughout the network. So it sends to Bob and Charlie, which are his immediate neighbors. And Bob and Charlie are both connected to Alice, but none of them know that. None of them know the network topology. So the natural thing for them to do is to gossip, right? It's just to flood the message. And at the end of the day, both of them send the same transaction, which is 0x ABCD1234 to Alice. And Alice received the same message twice, which is redundancy because Alice only needs to learn about the message once. So I think Pop was mentioning Gossipsub v2, which would include I announce messages. And however, I think the point is that announcing inventories, announcing like the messages that are available to send with say shorter hashes is not always optimally efficient. I think in almost every case, it's a very practical solution. And it's, I think, a very robust and practical solution. But I think the point here is that when the actual messages that you are trying to send is short enough, and when you have enough peers, then these I announce messages can also constitute significant overhead. Because, for example, here, suppose that Bob, Dave, and Charlie all have the same message to send to Alice. Suppose that the message is, again, 0xABCD1234, and the hash of the message is 0xbeef. So Bob, Dave, and Charlie would each send an I announce message to Alice. And so this is already 12 characters, and the actual message that Alice wants to receive is only 8 characters. So it's kind of a motivating example of when this kind of signaling or protocol messages can cause overhead, especially when the actual stuff to be sent is very short. So let's try to kind of abstract this problem a little bit. So the problem here is for Alice. So kind of let's kind of try to isolate this problem to just one pair of peers, like Alice and Bob. So the problem here is for Alice to learn only the new items from Bob, and vice versa. So here, for example, Alice holds a set of items that she intends to flood to Bob, and Bob also has a set of items which is B that he intends to flood to Alice. So we realized here that there's significant overlap between the two sets. Both items A and B are present in both sets. So actually, Bob only needs to learn about C, and Alice only needs to learn about B. So the problem here is to figure out that fact, because Alice did not really know the content of Bob's set and vice versa. So it's actually very tricky for Alice to just figure out that, hey, Bob is missing C and I should send C to Bob. It doesn't work, right? And I guess sending I announce messages is one way to make it work. Basically, Bob can kind of describe what's the content of his set using succinct identifiers like hashes, but as I mentioned, when the actual items are short, the hashes are not much shorter than the actual items, and you don't save a lot of bandwidth here. So this problem of having two parties learn about the union of their sets is called the set reconciliation problem, and the kind of the definition here is a little bit quirky, because based on the definition, only one of the two participants, like Alice or Bob, needs to learn the union of their sets in order for this process to be declared successful. But it doesn't matter too much, because once, say, Alice receives the union, she can always send the union to Bob, because she will actually know which items are missing on Bob's side. So I think this talk is kind of trying to be like an overview of what's possible with set reconciliation. So let's first define like a parameter of this protocol, which is the size of the symmetric difference of their sets, which we denote as D. So here, D is the number of items that are exclusive to only one of the participants. For example, here, the size is 2, because the symmetric difference is just C and D. So here, the parameter D, the size of the symmetric difference is 2. And set reconciliation is, I think, is a very fascinating problem, and it's first proposed in a paper back in 2003. And within the paper, the authors actually proposed a kind of information theoretically optimal solution. So which I summarize here on the first line, which is Alice and Bob can finish set reconciliation when, after communicating exactly the same amount of bandwidth or the same amount of data as D items. And if you think about it, it's really the information theoretical lower bound, because one of the participants needs to learn about the symmetric difference in order to reconstruct the union. So if the person is learning D items, then it makes sense for the person to receive the amount of communication or the amount of data, right? So it's communication is very efficient. However, there's a kind of a catch, which is it takes quadratic computation, and when the size of the individual items are large, and also when the number D is large, is actually quickly adds up. So the second paper, which is one from 2011, proposed a kind of a different scheme in solving this problem, which successfully brought down the computation cost from quadratic to log linear, which made this scheme very practical, and it also retained somewhat the kind of the information theoretically optimal communication bandwidth. It adds a very small factor, maybe 2 or 3, in front of the number D when it talks about communication cost, but it's still quite efficient. The caveat here is that the protocol requires pre-knowing or pre-guessing the size of the symmetric difference or the number of differences that it's trying to reconcile. So it's kind of a pretty much impractical thing to use in real systems. So the third paper, which is the one supported by the EF, brought this solution to the state of the art, basically removing the requirement to pre-know the number of items to reconcile. So basically, now reconciliation is as simple as, say, Alice sending a stream of data to Bob, and Bob can say stop when it receives enough symbols or when it receives kind of enough information for reconciliation, and that's it. So to recap, the communication cost of state-of-the-art set reconciliation is kind of a small parameter, a small coefficient times the size of the difference to reconcile. So here the actual coefficient is 1.35, and we can even bring it to about 1.10 if we use more sophisticated algorithms, but I'll leave it as kind of future discussion. And the computation is log linear, and according to my experiments, you can achieve tens of megabit per second per CPU core in a somewhat kind of outdated server CPU. So it's not very beefy CPUs. And it only takes 1/2 of a round trip or a single trip for reconciliation to finish, because Alice can just keep streaming the symbols, and Bob can just tell Alice to stop whenever it finishes. And also maybe piggyback with the items that Alice should learn about in order to reconstruct the set union on her side. So I'll just spend maybe 1 minute talking about the basic idea of how reconciliation is done. So let's kind of consider a very special case when Alice and Bob's sets differ by exactly one item, and let's just kind of attempt that we can encode the items into integers. So here in this example, Alice has 4 numbers and Bob has 3 numbers, and there's one number that only Alice has, but Bob does not. So Alice can calculate the sum of her items, and Bob will calculate the sum of his items. And Alice can just send this sum to Bob, and Bob can just compute the subtraction of the 2 numbers, and he can reconstruct the number that he's actually missing, right? It's just arithmetics. So when we want to generalize this basic idea to scenarios where A and B do not differ by exactly one item, then it gets a little bit trickier, but it's still doable. And the main challenge here is to kind of figure out how to group those subsets that you sum up, and how to basically how to group the subsets to sum up, and how many such groups or how many sums do you send over the communication channel. And for a formal treatment, I would recommend taking a read of section 3 of this paper. I think it's less than a page, or we can watch the first 5 minutes of this video. So I will skip this part because it's just a kind of a demonstration of how to apply this to signature aggregation in Beam chain. So basically, you reconcile the sets of unaggregated signatures among the nodes with the aggregator. And as a kind of a quick detour, I'll mention that second set reconciliation has been is going to be deployed in Bitcoin. There have been 2 proposals. One's called Erlay and one's called Graphene. And both of them try to use set reconciliation to make transaction propagation more efficient in Bitcoin. Because if you think about it, transactions are exactly the type of data that are short, but are a ton of them, and you really want to worry about the cost of signaling, like those unannounced messages or those INV messages in Bitcoin talks. So the idea here is that to reconcile the hash rate of the transactions in people's memory pools instead of flooding them. And this particular proposal, which is early, is already implemented in Bitcoin Core actually a few years ago. And the last time I checked, there's a, I think, March 2025 or March this year update, I think, saying that it's progressing towards deployment in Bitcoin's mainnet. So to summarize quickly, the status of set reconciliation is that an implementation of the state-of-the-art scheme that I described is more or less ready. Again, supported by the Ethereum Foundation. So yeah, really appreciate of the support. it's in Golang, and there have been community like volunteered implementations in C++ and Rust. I think it's also being incorporated in some of the frameworks for building efficient distributed systems. I think as a next step, some simulations need to be done, and we need to kind of measure in the particular case of beam chain and signature aggregation, does it actually make sense to use set reconciliation, and how much gain potentially can we make compared to, say, Gossipsub? And there are a few open questions, I think. For example, the topology, I think, do we use grid? I think grid is kind of a very promising topology, but because it's very structured, and yeah, so we should also incorporate that into the simulations and do some tests. And kind of an off-topic point is that other applications in the Ethereum ecosystem or other applications of libp2p may also benefit from this scheme. For example, I performed an experiment trying to do state healing using set reconciliation instead of walking interactively the Merkle trace, and this reduced number of interactions, basically there's only one round of interactions, really helped in terms of saving the overall job completion time. So I will stop my talk here, and I'm happy to take questions.
Thank you, Lee. Sorry, go ahead if there's any questions.
Yeah, I actually have it's related to the discussion of simulations, and I understand at one level that's sort of at most of what people have right now. There's some test implementations, but a lot of it is simulation. But I wonder a little about a tail wagging dog aspect to some extent. I understand it's much easier to test things if you have solid, reliable simulations. But I mean, multiple speakers. I don't mean to pick too much on this one, but this comes up prominently. I don't think it's that bad a target. Have emphasized how much easier it is to simulate. I mean, yes, it's better in other ways too. But one of the main ways some of these are better is they're easier to simulate. Okay, great. But is that, let me say, how relatively important should that be? I want to kind of pose this as a question in terms of picking a protocol. Is the answer to make better simulation tools a little glibly?
Interesting. So if I think it's a very valid question, and if so, it's kind of I think my habit is to simulate first, because it's always good to fail early. And if simulation tells that, hey, there's some significant issue with a scheme, then I would say that running a simulation in, say, OMNet++ or NS2, NS3 is much lower cost than doing an actual deployment, or doing an actual implementation and like setting up like an emulation, like real deal networks. Yeah, so is it a correct understanding that the alternative would be more theoretical study, or more like real deployments or real implementations?
Well, I guess what I had in mind was like, to what extent is this a question of the simulations are challenging but feasible, or to what extent is it that certain of these protocols, let's say the Gossipsub as we have it today, or generalized Gossipsub as Age was, I think, right, presenting it, are just borderline unsimulatable versus what is it that are more tractable simulations? I think I'm still thinking within the realm of simulation here, because I do agree that it's a very valuable tool, and theory and full-on deployment have their place, but simulation is a great middle ground. But is it just like 10% easier, or is it feasible versus not feasible?
Very good point. I see. I think it really depends. I think for Gossipsub, I think it's way more advanced than some of the ideas, including the set reconciliation idea proposed in the scheme. Because even though, say, set reconciliation, you have the library to kind of to use, you don't really have an end-to-end like executable. But it's not the case with libp2p. I think there was a very interesting point made in the Beam research Telegram group. I think someone proposed a a very nice tool that can just run unmodified Linux binaries in the simulator, and the simulator is going to simulate a network for you, but you just supply it with an unmodified original binary, which we already have for Gossipsub. So I think for Gossipsub, I think simulation is, per my understanding, it's borderline no cost, and I think it's a very cost-effective way to verify a potentially very large scale of protocol deployments. I personally ran a few experiments involving more than 1,000 AWS servers, and I burned, I think, 50K of my advisor's funding because of that. And then I started to kind of just switch to simulations first. On the other hand, for those newer protocols, from my experience, simulation is, I think, 20 or 30% of the cost of doing a proper implementation, because you can worry about much less stuff because you have a very nice environment. There's never connection drops, and you can just focus on writing the core state machine and not worry about like writing the boilerplates, like connecting to like opening up sockets and like maintaining connections, error handling in particular. So yeah, that's my limited experience, like 30% of the cost of an actual implementation. Yeah. Yeah, I'm not sure if that answers your question. Yeah, I mean, 30% is quite something. Yeah.
Yeah, no, no, absolutely. It quantifies it in exactly the way I was looking for. Yeah, thanks.
Lee, thank you so much for the presentation. One question I
thanks.
have, but I'll ask it offline, is, does this help when the messages are very small versus very large? And I think in our use case, we have very large messages, and so quantifying the possible improvement is something I'm curious about. One of the things that you mentioned was that we have this Telegram group. So it's the Beam peer-to-peer networking Telegram group. It's a relatively small group with 29 members right now. If you are interested in contributing to the peer-to-peer networking layer, do send me a message and we can add you to that group. Okay, so now we're going to just close off with two smaller presentations on implementations of libp2p. The first one is Mihir in implementing libp2p in C, and then Bing in Zig. Mihir, the floor is yours.
Yep, thanks, Justin. I'll just share my screen. Yep. Okay. Let me know if you can see the screen. And
yep, can see the screen.
Yep. Okay. Yep. Hi everyone. My name is Mihir, and I'm from the Peer2 team. In this presentation, I want to give a brief overview of the progress we've made in the C implementation of libp2p. So basically, we started development of the library on 7th of March, and this week we actually made the repository public on GitHub. We ended up starting with the multi-formats modules and have implemented these modules so far. For the multi-base module, the implementation only supports all the base encoding formats that have the final status in the multi-base specification, but we will definitely add support for more base encodings if needed in the future. For the multi-hash module, we have currently implemented all the common SHA support for common SHA functions, except for SHA-1 as that has been deprecated. But again, we can definitely add support for more functions if needed. And also for the CID module, we implemented support for V0 and V1. At the moment, we're still making progress with the multi-address module and as well as the peer ID module. The core functions have been implemented. We just need to verify the correctness with test cases and ensure that they can pass on multiple different platforms. And once work is done on these modules, we'll be able to focus on implementing these modules here the to-do ones. I'm sure that I may not have mentioned, Gossipsub, but we also do plan to support that as well, definitely. Our goal is to basically get the library to a state where it supports enough modules such that it can be used to be able to interact with any beacon node in the Ethereum's consensus layer. Once we have, robust implementation that has been thoroughly tested and works on multiple different platforms, we'll be happy to start sort of prototyping any new protocols that are being developed for the Beam chain. Regarding contributions, because the library is still at a very early stage of development, it is not yet intended for public usage, as there may be some continuous changes to the API. Like for the modules that are currently implemented, I'm expecting that not to be the case. But there is just a bit of slight risk that the API may change. But once we have finished implementing all the core modules, we'll provide usage documentation for the API, and then we'll be happy to accept any feedback for improvements, or if there are any errors with the library, we'll be happy to accept any pull requests. But yeah, just thank you, everyone.
Amazing. Thank you so much, Mihira. Any questions? Okay. Thanks again, Mihira. And yeah, looking forward to this implementation blossoming over time. Bing, the floor is yours.
Yeah. Can everyone see my screen?
Yes.
Right. So yeah, thanks for having me on such short notice. I'm just here to share a bit about the P2P. We are currently building this out at Zenith. The work is mainly done by Grape Baba or Kai Chen and me, Bing. So I just want to keep this short and sweet, just to share what we currently have done and what we are focusing on next. So currently we have on this slide, you can see this 3 core projects that we have been working on: multi-formats, noise protocol, and Yamix. 2 of the first projects are more or less done. The current focus is kind of on Yamix, as well as working on adding examples to noise protocol to demonstrate the library usage. All of our work is open source and discussed at github.com/zen-e. Feel free to follow us on GitHub and join our Telegram group. DM us if you have any questions. And yeah, one thing I didn't mention is that our near-term goal is to eventually pass all the interop test plans that's provided by the P2P tool. So if you're interested in Zeem and Zik in general, feel free to follow us and join our Telegram group. Thanks.
Thank you, Bing. One thing I'm curious about is, how are you guys funded? My understanding is that Zenith is like a pure public goods entity, and I only just learned about the team recently.
Currently, we're just doing this sort of like in our own time. Yeah.
Okay, amazing. Thank you so much, Bing. So any questions for Bing? Yeah, Gajenza says go Zig in the chat. If there are no questions, this concludes Beam call number 3. One thing I do want to mention at the end of this marathon call is that there is a Telegram group for the Beam calls. All of the devs and the researchers should have been invited. If you are a dev and a researcher and you're not part of that group and you do want to be, do send me a DM. In addition to that, anyone who joins 2 of the Beam calls also gets invited. So if you're watching this and you made it to the very end of this video, congratulations. If you've joined 2 of these calls as an attendee, you're also welcome to join this group. That's it, folks. See you next time for Beam call number 4. Thanks. Bye.
Thank you.
Thank you.